Dear colleagues, good morning. Let's start our morning session. The first speaker is Alexander Philippov with his talk on pulsar magnetospheres.
Thanks. Good morning, everyone. It's early morning, so I apologize if I'll go very slowly or do stupid things. It's not the time I usually do talks, so I encourage everyone to ask questions so everyone get awake and energetic. So my title today is How Do Pulsars Shine? That's my thesis work done in Princeton. Anatoly Spitkovsky is my thesis advisor. A bunch of other people contributed to this research. Benoit was at Princeton doing the some sort of peak simulations with us. Sasha Chekhovskoy was a postdoc at Berkeley. He contributed to the force-free work. Dmitry Zdansky recently did some interesting stuff about giant pulses with him, and two string theorists which we got on board to explain some analytic results from Harvard and former Harvard, now Arizona. So I gave a talk about pulsar magnetospheres at the previous conference in 2014. It was mostly the force-free stuff at that time. And there was one paper about kinetic modeling, this one, being published. But I promised you we're going to explode the field, and this is what happened. Over 3 years, around 20 simulation papers are published. There are a few analytical papers trying to explain the results that we found in simulations. We are now modeling both the magnetosphere and the emission physics with this kinetic model, so we went pretty far. I think it's ultimately the best time to do pulsar theory since the ancient time in the 70s when the giants started to wrap up the field after the pulsars were discovered. The same US places are involved: Princeton, Harvard, Berkeley, Columbia, NASA Goddard. They're all running this expensive kinetic simulation starting from from our paper in 2014. And another motivation to do this theory now is that with this exciting discovery of fast radio bursts, we unraveled one more mechanism of this coherent radio emission. And it definitely calls for reconsidering of all these models that which were constructed in the 70s with analytical models. Now we have much more powerful techniques, numerical simulation, and we should definitely reconsider all the models about radio emission now. So I'm going briefly through the introduction just for someone who last saw the cartoon of Pulsar back in the grad school. So this is a 10-kilometer neutron star spinning around this axis. There is magnetic field frozen inside this conductor. It spins. There is a phenomenon called unipolar inductor, which when you rotate the conductor in magnetic field, you generate voltage. Part of this voltage points along the magnetic field, so it pulls out charges from the neutron star atmosphere. They accelerate along these field lines. When particle is accelerated along the curved field line, it emits a curvature photon. This curvature photon is depleted in the 10 to 12 Gauss field into a pair. And then this pairs also emit synchrotron photons. They are freshly accelerated, they emit new curvature photons, and this is like a cascading process. You produce more photons, they do more pairs, and this self-sustains itself. So the process runs until the point where this accelerating field would be screened by plasma. So when you try to put plasma in electric field, what it wants to do, it wants to screen this electric field. You create charge separation, and this charge separation creates an electric field opposite to the electric field, which was accelerating charges in the first place. So these are two mechanisms how you get plasma around these neutron stars. You get charges from the atmosphere, and you get pairs from this cascading discharging process in vacuum. So the problem becomes extremely complicated. We started from a dipolar field, more or less. We rotated the star, but now there are charges around. There are these atmospheric charges and the electron-positron pairs from the discharge. So they drive currents, they drive charge densities. These currents and charge densities modify the field structure, so it's a coupled, highly nonlinear problem. You need to understand how these charges are produced in order to study the feedback on the magnetosphere. So we observed the sources across the whole electromagnetic spectrum. They were discovered in radio waves. Recently, 10 years ago, Fermi was launched, and it discovered the whole population in gamma rays. More than 100 sources up to now. And what's most interesting about these gamma rays is that the efficiency at which pulsars convert the rotational energy of the spinning star into these gamma rays is very high. So usually you find something from 1 to 10%, And this is a significant fraction of the energy budget. So supposedly, if you understand the gamma rays, you would understand the significant part of the energetics which happens around these sources. So the open questions about this cartoonish picture is how this machine actually works, with details, with where these particles are accelerated, to what energies, what emission mechanisms are at work to produce all this emission. And we have this well-known clue from observations of nebulae that if you convert the synchrotron emission from the nebula into number of particles, you'll find what we call a plasma field magnetosphere. So plasma with a reasonable density to produce a large feedback on the magnetospheric structure. So vacuum models are not reasonable. We need to do plasma field magnetospheres. How particle acceleration works, how they shine, this should all be understood from the theory side, and how pulsars evolve would be also a good question to ask. So the cartoon picture for the magnetosphere was invented in '69 by Goldjack, though I will show that this model is actually not working. The concept that they introduced is that you pull out these charges from the polar cap, the region where these open field lines which stretch out to infinity start, and you drive this charge-separated current of electrons along the field lines. So you pull out electrons, you pull them, and they stream along the magnetic field. You get this current, and this is like a current wire. So you have your wire, you create a toroidal field around it. So this is a toroidal field around the wire. And also, since the thing rotates, the plasma wants to co-rotate with the star. And the minimum charge density that you need to have to support this co-rotation is what's called the Goldreich and Julian charge density. This is just a divergence of V cross B, where V cross B is just the electric field which is created with co-rotation. So this is the minimum charge density. The electric field you create is along theta, more or less. So this E theta cross this B phi is a Poynting flux, which carries the energy in the form of electromagnetic fields away from the pulsar. This is our Poynting flux. And then this current closes on the surface of the neutron star. When the current closes on the surface, it crosses field lines. It flows like this one, while the field is more or less radial. You have a non-zero J cross B. This applies an ampere force on the star, and this slows the rotation down. So this is a key idea, that you drive the Poynting wind, and this produces energy losses. It took 40 years to actually provide a quantitative paradigm for this picture. This is a well-known decade-old simulations in force-free. So in this picture, this is a time-dependent simulation of the aligned pulsar. The magnetic and rotational axes are aligned. You start from vacuum, you rotate it, and this is what you find. You find the most of features that I outlined in the previous slide. You get this closed field line region, you get open field lines, which are stretched to infinity. They meet up around the light cylinder, the surface at which if you want to co-rotate with the star, you'll have to co-rotate with the speed of light. So this is a characteristic magnetospheric size. After the light cylinder, the field lines are mostly radial, so they approach what's called the split monopole regime. And the toroidal field on these field lines, which is produced by these currents, they meet up at this equator, so you produce a discontinuity. And this is what we call the current sheet. So the flipping polarity of the magnetic field needs to be supported with current, with this very strong current. And this is where reconnection happens and the strong current flows. Also, there is a discontinuity at the boundary of the closed field lines. There is a toroidal field here, but there is nothing here. So you create this separatrix layer, a region of the volume of the separatrix return current. So this is how the current closure happens. You drive this current along this field lines outwards, and this is how it closes up, along this current sheet and the separatrix around the boundary. So I'll not go into details how it was done. This is already well known since 2006. And this is an extension to oblique rotators, where the magnetic axis and rotational axis are not aligned. Topologically, you find very similar structure. You get still this closed lines, open field lines. The current sheet is now no more a plane. It's a complicated rotating and undulating structure. So once the pulsar rotates, the current sheet undulates around the equatorial plane. So it's not a stationary structure, but otherwise it's pretty similar to the line rotator. What was most exciting that this amount of the spin down that the pulsar loses in forms of this electromagnetically dominated wind, you can actually quantify it as a function of rotation rate, magnetic moment, and the inclination angle. So there were many controversies about how pulsars spin down. This is the answer in the force-free regime. This was very exciting, and you could ask me why I'm here, why I'm giving this talk. And the answer is that the previous models were good in identifying the magnetospheric structure. So the field structure was much more understood than it was in the 80s and 70s. However, these most important questions about where particles are accelerated, where the emission is produced, could not be answered, because the force-free is like a plasma physics for poor people. It's plasma physics without any plasma. So the equations didn't know anything about the plasma. They were completely governed by electromagnetic fields. So you need to introduce these particles back in order to say something about their acceleration and emission. And this summarizes what can be done with MHD and what can't. So if you want to simulate effect of charge densities and currents on the magnetospheric structure you find with MHD, you can do also temperature of plasma and the inertia, which are important in these current sheets where the B field goes through zero. All these effects start to become important. But most interesting stuff, the non-thermal particles and plasma instability, so this is relevant for gamma rays and this is relevant for radio emission, this could not be understood. You need a more first principle model. So the method that we're using is what's called the particle and cell simulation. So the core of this is a well-defined algorithm for doing fusion plasma and most recently the astrophysical plasma. So this is a technique which allows to solve Maxwell's equations and particle motion more or less consistently. So what it does, it solves these two time-dependent Maxwell's equations and equation for particle motion in the following way. You start with some particle distribution and some initial distribution of electromagnetic fields. Once you have A and B, this equation is well defined. You can solve for new velocity at new time steps. So this is this block. Then over all these particles, you can extrapolate to the grid and find charge densities and current densities. And they are sources for Maxwell's equations. You go and solve them, and you get your new force. You interpolate to particle position, and you continue this loop over and over again. So this is how the core method works. In order to simulate magnetospheres, you need many improvements. You need this conducting star sitting in the center. It's a challenge to do on the Cartesian grid, which is the most usual thing in these codes. You need good outflowing boundary conditions. You need this atmosphere of charges which are sitting on the surface of the conductor. Also, you need to understand radiation, and since it's a very fastly cooling regime, the B field is very, very large, the cooling effect, the cooling feedback on particles is important. And here you can ask me, you said I'm running Maxwell equations with like Lorentz force, the radiation should be all there. However, this high frequency radiation, the synchrotron radiation by relativistic particles, the frequency is boosted by gamma squared. So if you're usually resolving the gyrations of particles with a few time steps, the frequency of radiation is gamma cubed times the Larmor frequency. So it's hopeless to resolve it on a grid. We need some sort of a subgrid model. And luckily, we know the answer. This is just the expression from Landau-Lifshitz. You just subtract the energy that particle emits in radiation, you deposit as a photon, and you can track these photons on the grid. And these photons, they can do pair production, so there are two channels. First, you get pair production in this high B field that I outlined on the first slide. And in many pulsars, the process in the outer magnetosphere, the pair production and photon-photon collisions are also important, so we also simulate that. It turned out that GR effects are important. This was very exciting, and I hope to be able to come to that. And this briefly tells what the scales we can simulate. So as usual with computer simulations, you're usually not powerful enough to fit the real parameters. However, what's mostly important is to keep this hierarchy of scales. So the tiniest scale in the problem is the Larmor radius, but this is so tiny that I'm even not talking about this. So the plasma skin depths at which this plasma physics processes happen, at least the process of screening the electric field in the polar gap. This is the skin depth, then there is the radius of the star. So for usual pulsars, this is like 1 centimeter, this is 10 kilometers, so 10 to 6 separation of scales. Of course, we are not able to do this on the computer. However, we can do still reasonable. We do 30, like up to 50 in 3 dimensions, and in 2 dimensions we do up to 1,000. That's a lot. So there is still a big number here sitting, much larger than 1. The light cylinder to stellar radius, so this is also the several hundreds. So starting from force-free simulations, what we are able to simulate is from 3 maybe to 10 in 3D, and in 2D we went up to 1,000, up to 100. So this is a big number, and we find that if this is larger than 2, then you actually get the asymptotic regime where the exact number doesn't matter much. So the potential drop, the amount of voltage that the particle can gain in this electrostatic gaps near the surface, particles can get up to a very big Lorentz factor in real pulsars. So we simulate something like 500, and the Lorentz factor at which they start to produce pairs is 40. Still much less than this one. If particles can accelerate, they will accelerate and they will produce pairs. Later in this talk, I'm describing efforts that have been done in order to produce reasonable solutions of these magnetospheres. First, I'll start with the model which was postulated in Goldrich and Julian, just 3 particle escapes from the surface. Let's see how it looks like. And then trying to inject particles, this would be done by hand, just injecting particles all over the place, trying to see if we can reproduce what was found in force-free studies. And then I've discovered other regimes with realistic plasma supply, and this I'm going to outline next. So the first thing that you're doing, the particle escape from the surface, doesn't actually look like what Goldreich wrote. So instead of this particle wind extending to infinity, you find this trap solution. So this is an aligned solution, this is an oblique solution. What you find here is that electrons are bouncing back and forth in this region around the polar cap, and the positively charged particles are in these equatorial regions, not flying anywhere, even in the oblique solution. So the person who did it right was Kurt Michael in '85, and it was reproduced in more and more realistic simulations. So what happens here is that first electrons, they fly away, they carry the charge, and this neutron star is left with a net charge. So the quadrupolar inductor electric field actually pulls out electrons, but then it starts to feel this electric field of the net charge, and they are falling back and forth here. So they're not going anywhere. And this calls for oblique rotators as well. So there is a little drawback in this argument. This disk is actually unstable and can drive some outflows to infinity. However, the currents that you create are low, so they're still dead. I will not focus on that. So this was a regime where you got only particles from the surface. Here I was also introducing particles all over the place. And not surprisingly, what you find something close to force-free. You get closed field lines, open field lines, toroidal field of different signs meeting here at the equator. So this looks like a force-free model, and what it brings on top of the force-free model is how much energy is actually dissipated into particles from these electromagnetic fields. And you find that most of the dissipation happens in this current sheet where magnetic reconnection takes place, and within 2 light cylinders we are dissipating around 15% of the Poynting flux. So this 15% number is important for gamma rays, so keep that in mind. So the acceleration of particles in these current sheets happen with the usual mechanism. So the B field goes through 0 here, and you have electric reconnection electric field. Fortunately, I don't have much time to describe this process in very details, but hopefully you heard something about reconnection. You know that it creates electric field, and inside this current sheet, the B field goes through 0, but electric field doesn't. So E becomes larger than B. This means the particles have no way rather than accelerating. So they're accelerating along the electric field, and they're getting up to energies of the sigma parameter, which just describes that most of the electromagnetic energy has been dissipated into particles. This is how 3D structure looks like. The colored map is the mean Lorentz factor of particles. It highlights the current sheet. All over the place you see a dark thing, the Lorentz factor about few. But here you get accelerated particles with Lorentz factor about 10 and more. So this is about the sigma parameter of the light cylinder, which was reached in this solution. So this was all fun, but you can ask, why did I introduce particles by hand? You can do it better. You can describe the spare production process, which operates on plasma skin scale. And it provides these charge carriers for the large-scale magnetospheric structure, which lives at the light cylinder scale. And then this thing feedbacks on the plasma production region by defining actually the current and charges in that region. So what's important here is that you cannot zoom in on your favorite region, which was usually the pair production region back in the 70s, and study it in isolation from the magnetospheric structure. Actually, the magnetosphere, the largest thing in the problem, tells what happens in this pair production region, and the pair production region adjusts to it, to the large-scale structure. So I'll show more details later. This is how the aligned pulsar with pair production looks like. This was first done in this paper, and we confirmed this result in 2015 and extended it to oblique solutions. Right now, you find a pretty surprising thing. So here the black lines are poloidal field lines. You still find the field lines stretching to infinity, something that you've already seen from force free. You get this current sheet, this apparatchik layer around the boundary of the closed field lines. So it looks pretty much what you expected. However, these polar field lines are filled only with electrons. There are no positrons here. I told you that there is this acceleration process, pair production. Where is that? So the particles are just not accelerated in self-consistent solution. And the reason for that is the current that you create is lower than this charge density times C, which I described on the slide with Goldrake's paper. So the particles are pulled out from the star. They reach mildly relativistic velocities, and they're fine with driving this current, which is the charge density times velocity, and velocity is less than C. So the whole current is less than rho times C, and you don't need this particle acceleration to support this large-scale structure. So we do see pulsars aligned more or less with radio emission, likely with pair production. So this was a puzzle which we luckily been able to solve later. The first idea was that if you do oblique solutions, the pulsars with misaligned rotation and magnetic axis, you'll do better. In fact, you do. There is a region with both electrons and positrons over here. So you see electrons and positrons. However, the bulk of the polar cap still lives with only electrons. There are no positrons out here. So still, the current is less than the Goldrake-Julian, and nothing happens. The non-relativistic flow is supporting the large-scale magnetosphere. You can ask how this current sheet operates from the plasma physics point of view, and you find this usual instability. So if you start with a laminar current sheet, it starts to breaking into what we call plasmoids, the bunches of charge density and plasma density, and they're separated by regions of lower density, and this is where the electric field exceeds magnetic field. So in between these bunches, you get electric field exceeding magnetic field, and this is where particles are accelerated. And as I will describe later, this is the process which gives you gamma rays. So this is a zoomed in picture. You get this zoomed in. These are your plasmoids. Here they are in density, so there's much less density over here, and this is where electric field exceeds magnetic field. So the three-dimensional structure, how this current sheet looks in 3 dimensions, you see that the red thing is the current density, so that it highlights this current sheet. The surface is no longer laminar, it oscillates and wraps around, so these are the plasma instabilities which happen in the current sheet. So this slide just summarizes how the discharge operates. I told you that the important quantity is the current with respect to the Goldrake-Julian one. If it's less than 1, you're done with non-relativistic flow, which happens over a range of inclinations. So if you're semi-aligned, then current is sub Goldrake-Julian, and no pair production happens. So this was a puzzle, and the solution to that were the GR effects. So the solution here is that the amount of charge that you've been able to extract, it depends on the properties of the neutron star, the region which lives in the curved space-time. However, the current that you drive is set by the large-scale magnetospheric things, which lives in flat space at the light cylinder. So by introducing this frame dragging effect, which creates extra electric field due to rotation of space-time, you actually reduce the Goldreich-Julian density, you reduce the amount of charge that you can extract from this atmospheres, and this ratio starts to become larger than 1. So what's important here, even though this is a 20% correction, this is 1 divided by 0.8, and this is a runaway effect. If it's less than 1, you're fine with particles traveling less than c. If you're larger than 1, you run away and start to produce pairs. So if this is around 0.8, you divide by 0.8, you get 1. So 20% effects sometimes make a big difference. So this is the aligned peak simulation with GR effects included. You see a time evolution. This is electrons, these are positrons. It starts out in vacuum. Later on, it develops pair production, develops a separatrix layer, this current sheet. And once the whole current system is established, you see that this production of positrons near the polar cap, which is zoomed in here, happens non-stationary. So what happens here is that you extract these electrons. They're accelerated to moderate energies. They produce pairs. This pair starts to screen electric field. And the new charges that you pull out from the star, they're no longer accelerated to enough energies. And the pair production process ceases. You need to leave until this cloud of plasma leaves and the voltage is restored and new electrons are able to accelerate. So there is a limit cycle working on here. So you see that the polar cap operates differently depending on how the circuit is established. And I think this is very important for variability of radio on rotational timescale period, because the light crossing time between the light cylinder and the star is around a rotational period. So if you disturb the current sheet, you'll disturb a little bit the current fluctuations in this flux tube at the polar cap. So this would create variability in radio. So if you'll try to look for electromagnetic oscillations in this discharge tube, you'll actually find all over oscillations on all over timescales. So this, you can definitely see the long wavelengths oscillation. These are these oscillations which happen between the clouds. But there are also high-frequency oscillations inside the clouds, and these are the processes which work on the time scale of the screening of this electric field. So different people, when they look at this picture, they either say that radio emission is solved, like Yuri Lubarsky, or as I'm doing, I'm saying that you need to do more quantitative things. You need to do refined simulation of that and quantify the spectrum of that. But I think it's very interesting to find the radio emission mechanisms. And the key here is that the models back in the 70s, they were assuming some sort of a stationary flow, and we're looking for instabilities in that. There is no stationary flow. The flow is highly non-stationary, and you need to start from that in order to find the radio emission thing. So this is how it looks like in oblique geometry. This is a movie which is living in a co-rotating frame. So I'm sitting in a frame which co-rotates with the pulsar. In that frame, you find more or less a steady state. So these are electrons and positrons. You again find these clouds escaping. You see this non-stationary current sheet in action. Reconnection starts first when the current sheet is wide. It thins out, and when it thins out sufficiently, it produces this plasma instabilities and breaks into plasmoids. I have last 5 minutes. I'll not jump into details of the distribution function, but I'll mention that this return region is very interesting. You find the ions accelerated from the surface. You also get the positrons returning electrons from the Y point, and 2 streams of dense plasma. The very interesting region to find for like streaming instabilities in the current sheet as well. These are the few slides which summarizes how we did analytical studies of this GR polar cap. So right now we can predict where pair production happens analytically in GR for any field configuration. For example, this is a field where there was a dipole superimposed with quadrupole. So if you have your favorite model of the internal magnetic field, you open either this paper for a line solution or you open this paper for oblique solution. You find the current flows in the polar cap and the criteria, the current larger than the Goldreich-Julian, or these return layers tells you where the pair production happens. So they're very efficient and easy analytical technique at work. I'll not do this slide, but those who are interested in pulsar winds should notice that the wind is not only anisotropic in terms of magnetic field. So this was from MHD simulation, and the color is the toroidal field. So the field is highly anisotropic in latitude. But even more important, the plasma density is also highly non-uniform. You get these holes and low density regions and field lines which don't support pair production back on the surface. You get highly dense polar region connected to this pair producing part of the polar cap, very dense current sheet. So all over regimes happen here, and if you try to compute magnetization, it's also highly non-uniform. Where there is mostly no plasma, you get the most highly magnetized regions. Interesting thing about energetic ions that we found that the particles which are most accelerated in this magnetospheres are ions. They are pulled back at the foot point of this return layer at the boundary of the polar cap. They travel along the separatrix region. They gain certain energy. So the color here is the Lorentz factor of these electrons. And they're further advected into this current sheet and gain even more energy, and they're advected away. So if you look into spectrum, the most accelerated particles are ions. Positrons come next because there is a breaking symmetry here. The direction of the electric field in the current sheet has a preferred direction, so it accelerates mostly positrons. At highest energies, you only have positrons, no electrons. But the most energetic particle. This is like 10% of the full potential drop. So if you're in a millisecond magnetar situation, this could be very interesting for ultra-high energy cosmic rays. The interesting question is how these ions go away from the nebulae. I'm not addressing that. Other people do that. But this model provides a self-consistent scenario for acceleration of ions nearby the star. Okay, last 3 minutes, gamma rays. What Fermi told us is that they're mostly double peak. So you usually find this double peak morphology, and this is very easy to reproduce. The current sheet creates these caustics. The field line which points towards you at the same time, you create this caustic. So all the photons which are emitted along this field line, due to combination of rotation and expanding, they come at the same time. So this effect was well known geometrically, but now we have self-consistent simulations which provide the holistic beaming of particles, and you can compute this light curve. So the variability here is are these plasma instabilities which I described before. They happen on very small time scale, and with Fermi you observe like few photons per light curve. You'll never see these oscillations. You stack too many photons to see that. So you can quantify it as a function of obliquity. If you go into 30 degrees, the separatrix region is also important for the high energy emission. When you go to 60 degrees, there is not much happening over here. You generally produce this double peak thing, and with low obliquity, you also produce this bridge emission in between the peaks. If you cut the diagram like here, you produce some bridge emission. So all this morphology is more or less reproduced. And if you're a young student and you can actually work with data, you can actually try to look how the crab looks in gamma rays. And the student of Benoit actually did that. We're not trying to fit the exact shape now, but there's two parameters: the separation between the peak and the ratio of the asymmetry between the amplitudes between the peaks. So you fit this number, and you get the geometry. Crab is inclined at 60 degrees and 130 degrees viewing angle. So this is more or less consistent with what nebula tells us, and this is a good sign that this could be applied to other pulsars. So spectra, I don't have time to go into details. I don't have time to go into details of this either. But I'll just mention that I think that these giant pulses, which are actually usually coming from a different place rather than this polar cap emission, are coming from this highly non-stationary thing in this current sheet. So this is an isolated simulation of the current sheet. You see all this hierarchical structure of plasmoids merging and flying all over the place. And if you'll try to plot the pointing flux, you'll see actually waves leaving from here. And the physical reason there is very simple. You get these two plasmoids, which are actually bunches of current. They merge, and when they merge, they create an extra current sheet at the boundary, and this extra boundary, you have a time-dependent current. So this time-dependent current naturally oscillates and produces radiation. And most importantly, these waves are like fast waves at high sigma plasma. So there was a boundary of plasma vacuum here. These waves did not fill this boundary. They lived freely. And this is a good sign that this wave can actually escape. If you can ask me questions about why these are giant pulses, but I have no time for that. And these are my conclusions. Thanks for your attention.
Thank you for your interesting presentation. Some questions, please.
Jason.
Yeah, thank you very much for this very nice overview. So I'm not sure if I understood this correctly, but you seem to indicate that in some of your simulations, you're basically just introducing charges and then seeing how the magnetosphere responds. I don't have a good feeling for how computationally intensive this is, but is it possible to do that for a variety of charge densities and try and quantify at how much does the current density have to change to produce demonstrably different magnetospheric configurations? And I'm thinking about, moding pulsars here.
Right, so the simplest case where these charges are introduced by hand, you can introduce different densities. But the thing here, there are these bounds, the dead solution of the disk dome and the force-free state. You actually don't need much to produce a force-free state. The more you introduce, your currents would not change. They're bounded by this unique force-free solution. So there is not much region between the two. We actually simulated them in the paper with Cerruti in 2015. You find these pulsars transitioning between the disk dome and this force-free state. And what's more interesting, I think, is that when you try to do them self-consistently with realistic pair production, you find that they can bounce between this disk dome with no outflow, no spin down, and no activity, and this force-free state. So this could be some sort of nulling mechanism on few rotation scales.
Okay, thank you.
So, any questions?
Thank you, Sasha, for a nice talk. You mentioned briefly there is the application to NICER about the geometry of these hotspots.
Yes.
Can you mention what are can you predict the particle bombardment rates and the energy of the particles that hit the atmosphere?
So what I'll say is that you need distribution functions for that. And you actually need realistic multiplicity. So since we're bounded by this a little bit unrealistic parameters, we cannot really extrapolate yet to that regime. However, we can say that the significant amount of energy from this cascade goes back to the star. So for example, this is a phase diagram of the polar cascade. There are positrons falling back, and there are also electrons flying back from the previous episode. So you see the separated clouds. This means that part of the electrons which were produced fall back to the star. So something like about a few % of the cloud energy fall back to the star. And most importantly, you can do this return layers. We find this auroral electrons, like a similar thing which happens in Earth's magnetosphere. This thing you can easily predict. This is a Goldreich-Julian flux at sigma flying back to the Y point back. And this is the most important contribution for heating. So I think the return layers we can predict more robustly. For polar caps, we'll do refined simulations of this polar region and quantify these rates more. This results, the geometric results, at least tells you where you should expect these hotspots for a right range of parameters and range of geometries of the magnetic field. So NICER is looking at millisecond pulsars. We have no idea how magnetic fields of millisecond pulsars look like. You can stack your own model and try to see what happens.
So thank you again for your interesting presentation.